Good morning, everyone, and welcome. I'm Dr. S.K. Singh, holding a PhD, and I'm pleased to be here today. We'll be discussing water purification specifically for pharma and API manufacturing. In this presentation, I'll walk you through the key aspects of ensuring high-quality water standards in our industry. We'll cover the importance, the process, and best practices. So, let's get started and explore how we can achieve excellence in water purification for pharmaceutical applications. When it comes to water purification systems, one of the most important steps is selecting the right method of purification. This decision depends on a variety of factors, and it's crucial to choose the most appropriate approach for the specific needs of the project. Next, we need to think about the sequence of purification steps. Getting this sequence right ensures the water is treated efficiently and effectively, optimizing the overall process. Several key influences impact our choices here. For example, the water quality specification tells us what level of purity we need to achieve. The feed water quality is also critical, as it determines what contaminants are present initially. Additionally, we must consider the reliability and robustness of the treatment system. A system that's durable and dependable reduces downtime and maintenance, which is vital for ongoing operations. Finally, supplier support, along with maintenance and operation costs, play a significant role. Choosing a system with good support ensures we can keep it running smoothly over time without unexpected expenses. All these factors come together to help us design a water purification system that is effective, sustainable, and aligned with the overall goals of our water treatment project. Let's take a closer look at some of the key considerations when evaluating water purification systems. First, we need to consider the sanitization method used, ensuring it effectively eliminates pathogens and maintains water safety. Next, the reliability and robustness of the water treatment equipment are crucial. We want systems that can operate consistently under various conditions without frequent breakdowns. Efficiency or yield is also a vital factor. The system should produce the required amount of purified water without wasting resources. Supporting and maintaining the equipment is another important aspect. A system that's easy to service can save time and reduce costs over its lifespan. We also have to think about operational continuity. How well the system can run over hours, days, or even years, including planned downtime for maintenance. And finally, total life cycle costs, which encompass not just initial investment but ongoing expenses like energy, consumables, and maintenance. All these factors are influenced by several key elements. For example, the final water quality specification sets the standards we need to meet. The quantity of water required by the user impacts system design. The feed water quality and how it varies seasonally can affect system performance and maintenance needs. Additionally, the availability of support facilities, such as raw water sources, electricity, heating steam, chilled water, compressed air, sewage disposal, and exhaust systems, are essential for reliable operation. Overall, selecting the right water purification system involves balancing these factors to meet your specific needs efficiently and sustainably. When considering the physical aspects of setting up a water treatment plant, there are several key factors to keep in mind. First, we need to think about the ability to collect samples effectively, which is crucial for monitoring and maintaining water quality. Next, the space available for installation plays a big role, ensuring there's enough room for equipment and future expansion. Structural loadings on buildings are also important. We have to make sure the existing structures can support the weight and vibrations of the plant. Access for maintenance is another critical point. If maintenance is difficult or unsafe, it can lead to operational issues down the line. We also need to plan for the chemicals used in regeneration and sanitization, making sure storage and handling comply with safety standards. Location of the plant room matters, especially in relation to temperature control. Some processes require specific temperature ranges to operate efficiently. When it comes to leachates and adsorptive contact materials, we must consider how these will interact with the water and the environment, ensuring safe disposal or regeneration. Hygienic and sanitary design principles are vital to prevent contamination, and we must also address potential corrosion, leakage, and the proliferation of microbiological organisms. Proper cleaning and sanitizing procedures are essential to keep everything functioning optimally. Capacity and output requirements should align with the demand, so the plant can meet current needs and allow for growth. We also need to plan for instruments, test points, and sampling locations. These are critical for ongoing monitoring and quality assurance. Lastly, water purification system considerations include ensuring the entire setup integrates smoothly with existing infrastructure, is scalable, and maintains high standards of water quality. All these physical considerations are interconnected and vital to designing a reliable, efficient, and safe water treatment facility. Now let's take a closer look at the pre-treatment steps involved in water treatment. First, we have primary filtration and multimedia filtration. This stage is crucial because it removes larger particles, debris, and sediments from the water, helping to protect the subsequent treatment processes. Think of it as the first line of defense, making the water cleaner right from the start. Next is coagulation or flocculation. Here, chemicals are added to the water to encourage tiny particles to clump together, forming larger flocks. These larger particles are much easier to filter out later on, which improves the overall efficiency of the treatment process. After that, we move on to desalination. This step is essential when dealing with saline or seawater sources. Through processes like reverse osmosis or distillation, we remove salt and other dissolved minerals to make the water suitable for consumption or use. Following desalination, we have softening. This process reduces hardness caused by calcium and magnesium ions, preventing scale buildup in pipes and equipment. Softening ensures that the water is not only clean, but also better suited for various applications, extending the lifespan of plumbing systems. Together, these pretreatment steps set a solid foundation for producing high-quality water, aligning with our overall goal of efficient and sustainable water management. Now let's talk about how activated carbon, or AC, works in water treatment. First, it's great at removing chlorine, which is often added to disinfect water. However, once the chlorine is gone, bacteria can start to grow, so we need to consider additional steps. AC filtration is also effective at removing organic impurities, which helps improve water quality and taste. But there's a trade-off with certain chemicals like bisulfite. While bisulfite can leave behind sulfate residues, it has the advantage of being antimicrobial, meaning it can help control bacterial growth. When it comes to removing chlorine, we generally rely on either activated carbon filtration or bisulfite treatment. Both methods are valuable, but they serve different purposes. Activated carbon is excellent for quick removal of chlorine and organic impurities, while bisulfite adds an antimicrobial benefit, though it may leave some residues. Overall, understanding these options helps us choose the right approach to ensure safe, clean, and good-tasting water. Let's talk about the importance of routine monitoring of water quality. It's essential to regularly check environmental conditions, seasonal variations, and supply changes to ensure our water remains safe and consistent. When we notice any changes in the raw water source, treatment techniques, or system configuration, additional testing becomes necessary. This helps us understand how these changes might affect water quality and whether adjustments are needed. We also perform trend reviews, which involve looking at data over time to identify any significant shifts. If we see that quality changes are still within our specified limits, but differ significantly from previous results, we should review how we are using the water, whether directly as a finished product or as feed water for further treatment, and document this review thoroughly. Producing drinking water in-house requires us to have well-documented system configurations and water quality monitoring processes. This ensures we have a clear understanding of our setup and can quickly identify any issues. Now, when it comes to the actual production process, it begins with sourcing raw water, whether from a well, river, or reservoir. The water then undergoes various processes such as desalination and filtration to remove impurities. We might also soften the water, disinfect it using methods like sodium hypochlorite injection, or remove specific contaminants like iron. Additional steps can include precipitation or reducing concentrations of certain inorganic or organic materials. All these measures are integral to ensuring the water we produce is safe, consistent, and meets the necessary quality standards. Regular monitoring and proper documentation are key to maintaining this level of control throughout the entire process. When we receive materials in bulk or by tanker, it's crucial to identify any potential problems and risks right from the start. This helps us ensure the quality and safety of what we're working with. For risk control, we focus on several key areas. First, vendor assessment is essential, making sure our suppliers meet our standards. We also verify that certification activities are authorized and valid. The acceptability of the delivery vehicle is another important factor, as it can impact contamination risks. When it comes to starting materials, our system design plays a big role. It should allow for easy draining and sanitization, which helps prevent microbial growth. Using closed storage tanks with protected vents is a good practice. These tanks allow us to see inside easily and facilitate draining and cleaning, including the pipework connected to them. Controlling microbiological contamination is vital, especially in components like sand filters, carbon beds, and water softeners. We manage this through methods such as backflushing, chemical or thermal sanitization, frequent regeneration, and maintaining continuous water flow to prevent microbial buildup. Any changes made to the system must be approved by QA through proper change control procedures. This ensures that modifications don't introduce new risks. Regarding water storage, we need to prevent degradation by ensuring proper turnover and routine testing. This keeps the water quality consistent over time. Because this is part of an indirect impact system, it typically doesn't require full qualification, but we still need to monitor and control it carefully. Finally, the production of drinking water is a critical step. All these measures come together to ensure that the water we produce is safe, clean, and meets the necessary quality standards for our purposes. When considering factors for unmanned, remote sampling systems in power water applications, the first thing to look at is the water quality, including how it varies across different seasons and what the water quality specifications are. This helps us ensure that the system is tailored to handle the specific conditions we face throughout the year. Next, we need to determine the quantity of water required, which directly influences the design and capacity of the system. It's crucial to get this right to avoid under- or oversizing the setup. Then, we consider the sequence of purification stages and the energy consumption involved. Optimizing this sequence can lead to significant efficiency gains, reducing operational costs while maintaining water quality standards. The extent of pretreatment needed is another key aspect. Depending on the raw water quality, we might need more or less pretreatment, which affects both the complexity and cost of the system. Performance optimization is always at the forefront. We want the system to operate at peak efficiency, which involves fine-tuning various parameters to ensure consistent, high-quality output. Sampling points should be strategically located along the system. Proper placement ensures accurate monitoring and quick detection of any issues, maintaining overall system integrity. Finally, appropriate instrumentation is vital. We need reliable devices to measure parameters like flow, pressure, temperature, conductivity, pH, and total organic carbon. These measurements are essential for maintaining control, ensuring safety, and meeting water quality standards. All these factors are interconnected and ultimately support the overall goal of creating a robust, efficient, and reliable URS system for power water applications. On this slide, I want to highlight some of the key controls we can implement to ensure the safety and quality of our purified water systems. First, maintaining a minimum flow at all times is crucial. This helps prevent stagnation, which can lead to microbial growth. Next, Controlling the temperature within the system is also important. For example, keeping it below 25 degrees Celsius to inhibit bacterial proliferation. Providing ultraviolet disinfection is another effective measure. UV light can inactivate many microorganisms, adding an extra layer of protection. Additionally, it's beneficial to use components that can be periodically thermally sanitized. This means selecting materials and parts that can withstand high temperatures for cleaning purposes. Chemical sanitization methods, such as ozone, hydrogen peroxide, or peracetic acid, are also commonly used. These agents can effectively eliminate microbes, but it's essential to verify their removal during the process. Often, thermal sanitization at temperatures above 70 degrees Celsius is employed alongside chemical methods to ensure thorough decontamination. When it comes to producing purified water, especially at ambient temperatures, we need to be aware that these systems are more vulnerable to microbiological contamination, particularly when the system is static or demand is low. This is why having robust controls and regular sanitization at different stages of purification is so important. If chemical agents are used, we must also have proof that they are fully removed before the water is used. This ensures that no residual chemicals pose a risk to the end user. Overall, implementing these controls effectively helps us maintain high water quality and safeguard both product integrity and patient safety. Now, let's talk about the production of highly purified water, or HPW. This process typically involves a double-pass reverse osmosis system combined with ultrafiltration, or sometimes other qualified purification techniques. The key idea here is that we're using multiple steps to ensure the water reaches the highest levels of purity. The first step usually involves reverse osmosis, which effectively removes a wide range of contaminants. Then, a second pass through reverse osmosis can further reduce any residual impurities. Ultrafiltration is often integrated into this process to filter out particulates, bacteria, and some viruses, providing an extra layer of purity. The important thing to remember is that these techniques are based on the same principles as those used for producing purified water, but they are applied in a way that achieves even higher purity standards needed for sensitive applications. Overall, the goal here is to ensure that the water we produce is free from contaminants, making it suitable for demanding medical, pharmaceutical, or laboratory uses where purity is absolutely critical. Today, I want to highlight that distillation remains the preferred technique for producing high-quality water, and it's even recommended in some pharmacopoeias. When designing a distillation system, there are several key factors we need to consider to ensure efficiency and compliance. First, feed water quality is crucial because it directly impacts the purity of the final distilled water. We need to start with water that meets certain standards to achieve the desired output. Next, the required water quality specification and the quantity of water needed will influence the size and capacity of the system. It's important to accurately determine these parameters so that the system can be optimized for both performance and longevity. Another critical aspect is selecting the right generator. This means choosing the appropriate size and incorporating variable control. This helps prevent frequent start and stop cycles, which can cause unnecessary wear and energy inefficiency. Blowdown and dump functions are also vital. They help remove impurities and prevent buildup within the system, maintaining water quality over time. Cool-down venting is another important feature. It allows for safe cooling of the system without risking contamination ingress, which is essential for maintaining purity standards. Lastly, when producing water for injections, or WFI, these considerations become even more stringent. The system must ensure the highest purity level, meeting strict pharmacopoeial requirements. Overall, designing an effective distillation system involves balancing these factors carefully to produce safe, reliable, and high-quality water for medical and pharmaceutical applications. For further support, please contact us. We're here to help you with any questions or additional assistance you might need. Thank you so much for your time and attention today. Remember, we're committed to supporting you every step of the way.